All right, this is a review period before the exam tomorrow. Exciting. Exciting for the one person who's here. Hopefully it's also exciting for the people who will be joining later and couldn't make. All right, exam tomorrow. This is everything that could be on the exam in some way, shape, or form, some question written about any of these ideas. So what questions do we have?
I was hoping we could go over context-free grammars a little bit more. I guess I'm confused a little bit as to what the form of a context-free grammar is, or how you can identify a context-free grammar.
Yeah, so there are very few limitations to a context-free grammar. All we know is that on the left-hand side is a single non-terminal, and on the right-hand side is any number of terminals and non-terminals in any order.
Gotcha. And
There are very few restrictions there.
so that was Greibach's form, right?
So then there are two normal forms within that.
Okay.
So there was CNF, Chomsky normal form. That was either non-terminal to non-terminal, or non-terminal to terminal. Then there was Greibach normal form, which I don't even think is on here. But
yeah,
in case you wanted to, the only form for Greibach normal form is, how do I want to write this notationally? We have a non-terminal to a single terminal followed by 0 or more non-terminals. So these are all optional. So that's the only form in GNF. So either a single terminal followed by a non-terminal, single terminal followed by 2 non-terminals, etc. And those are both subsets of context-free grammars, which just say non-terminal to any number of terminals and non-terminals in any order.
that helps a lot.
And so CNF was used for CYK, the membership question. GNF was used for kind of creating the NPDAs directly from the grammar and vice versa.
Okay.
Those are the applications that we saw of each of those.
Would you mind scrolling to the first section of this note again? Here. A little bit lower, it might be an artist. Sorry.
So pumping lemma, context-free grammars, push-down automata.
So the CYK answers the membership problem. What problem does pumping lemma answer?
It answers, is this language not regular?
Oh, okay.
How to prove a language is not regular.
I was mixing that up with the CYK. But yes.
Yeah, CYK membership in a context-free grammar. Pumping lemma, being able to answer whether is a language not regular. The only way we can prove that is via pumping lemma.
Is there anybody to go over another pumping lemma problem by chance?
Yeah. That would be a very good use today. Let's bring up the exact. Yeah, anything from 5 or 6 would be the kinds of questions that might show up on on an exam. So I kind of want to go look at something from 6 because I like the ambiguity of is this language regular or not? Because now you have to think about, is there a DFA for this language? Is there a regular expression for this language? If you get the intuition that there is not, then you would proceed with the pumping lemma, because drawing a DFA is way easier than going through the entire pumping lemma process. Anything from 6 stand out, either something that was assigned or something that was not assigned that might be fun?
I was curious with D, you know, I think I got that one wrong in the homework.
6D. A to the n such that n is equal to 2 to the k for some k greater than or equal to 0. Great. That's a fun one. So when we see this, first question we can think of is this regular? Intuitively, I know, right? So what do we think for D? Intuition about, we're looking at 6D. Is this language regular? We need to figure out what the following languages are regular. And then to be able to come to that conclusion, we either have to show a DFA for it if it is, or we have to go through the pumping lemma if it's not.
Intuition alone, I could probably say it's not, but I don't know why.
So how many powers of 2 are there?
Okay, amount.
There are an infinite number. Yeah, so there's some k greater than or equal to 0 that's going to be infinite. We know some regular languages are infinite, but those that do have some kind of form where the loop allows us to add more and more and more strings into the language. And there may be multiple loops, which means there are multiple variables that create that infinite value. But now we need the concept of, is there some number of states that we could draw that would pump to make a number of strings in this language? And the intuition behind this is, since we need to consume twice as many A's to do this, there's no way we're going to be able to easily recognize that form. You can think of there being a loop that goes from like 2 to the 1 to 2 to the 2. That would consume 2 states as we go from recognizing one to recognizing that. But if we did that twice, we would end up with 6, which is not a power of 2. So every time we need to consume twice as many as we did last time. And we could recognize that by making, you know, a smaller loop, a bigger loop. It's not going to work with the limitations we have with a DFA. So this is a pumping lemma problem because this language is not regular. But how are we actually going to go through and show it? And I remember again that I did not upload yesterday's video. I was crazy busy until well into the evening here, so I wasn't able to do it, but it's very worth watching ahead of tomorrow. Sorry, Nathan. Very worth watching. We went through a pumping lemma proof. I took the entire class just drawing out everything. I'm going to be letting people resubmit those problems eventually because that last homework was pretty bad across the board, which speaks more to my preparating, like giving you preparation for that rather than any problem on your end. So we're doing 6D at the moment from the homework. What would the pumping lemma look like for a to the k, or sorry, a to the n, where n is 2 to the k. So some power of 2. We're going to accept all strings with a power of 2 number of a's. We're going to reject all strings with a non-power of 2 number of a's. So we're going to proceed with a proof by contradiction. So we would write something like, suppose L is regular. ST stands for subset. All right, there's that paragraph you can copy and paste for just about every pumping lemma proof, because we're going to assume the language is an infinite regular language. Therefore, we can break any string in that language down into X, Y, Z, such that the length of XY is less than or equal to M, the number of states according to the accepting DFA, and the length of Y is greater than or equal to 1, where Y represents the loop in the DFA that makes L pumpable and infinite. Great. So now we want to continue with this, and we want to find some W that is in the language. But we want to select something that is good. Note, though, that anything that we select here has to be in the language. What is something that we would want to pick for this? So if we did something like, yeah, like a to the m, then yeah, we can assign an m that is not a power of 2. But if we did a to the 2 to the m, then we know that 2 to the m, for all 2 to the k, is in the language. So we just substitute m for k, and we know that it's in the language. So sure, let's say, let w be a to the 2 to the m. That seems like one of the very few places that we could start. I can't even imagine another string that would fit in this language that uses m and is guaranteed to be in the language. That is simpler than a to the 2 to the m. I mean, yeah, we could go a to the 2 to the 2 to the m. We could get ridiculous here, but that's not going to help us. So now the next intuitive step is to think of, okay, within the first m characters of this, we have to see the x and the y. Which means the loop is going to be, just like before, just like in yesterday's example, somewhere between 1 and m a's. To make this a little bit easier, what is the power of 2 that is less than this 2 to the m? So is there another easier way to write a string that is a to the 2 to the m minus 1? How could we represent that in a way that's going to be more useful to us? The other one to think of is a to the 2 to the m plus 1. How can we simplify or make this more useful?
You think like a to the m minus 1, a to the m plus 1. That's better enough. You just give the 2 power.
So what does this represent? If we add 1 to this, how much bigger is this entire thing? How many a's are there? We could write out, if you don't know the rule off the top of your head, you can start to write it out. Something like, all right, a to the 2 to the m. What happens when m equals 1? How many a's are there? 2. 2 a's. When m equals 2, how many are in a to the 2 to the m? 4 a's. When m equals 3, how many are there?
6.
It's 8. Or 8 of them. Yeah, 2 to the power of 3 is 8. So now we can see that when we add 1 to m, we are doubling the size of this. So you could rewrite this as equivalent to a to the 2 times 2 to the m. It doesn't look simpler, but it tells us that there are twice as many a's in that version. So if we were to do something like select all possible y's between 1 and m, then what we're going to be doing is we need some way, some functional way to show that when we repeat that, we end up with something that's not a power of 2. We just need an example of one such I that is not like that for every possible value of y. So again, to write this out in a way that is going to be useful to us or a way that's easy to visualize, let's look at all possible values of y. So y could be the string a. Y could be the string AA, etc., all the way to a to the m. For each one of these possible values of y, we need some value of I that says that when we do this some number of times, we end up with something that is not in the language, regardless of the value of m. So what could we instantiate or what could we use to do that? How would we like to proceed to say, does it make more sense maybe to add some loops to this, subtract some loops to this, to sometimes we want to do one and sometimes we want to do the other? Let's take this case to start with, just to get an idea of what that looks like. This says that we have MAs at the front that are part of the XY breakdown. So let's just kind of draw out an example of that. We have, I don't know, for some value of m, I'm going to instantiate it here, but remember that when you write these proofs, we don't want to instantiate it. Let's say for the sake of fun that m is 3. If that is the case, then a to the 2 to the m is going to have 8 a's. We know within the first 3 characters here, we need to see x and y. The length of xy has to be less than or equal to m. So Z is the last 5 A's plus potentially some of these other A's. But we need to break down X and Y somewhere in here, which tells us there are 3 options for what Y can be. Well, I guess there's 4 options. Y can also be empty. But it can't if its length is going to be greater than or equal to 1 in the case of this string. So we know there is a loop somewhere in this DFA. Because there are only 3 states in the DFA, by the time we consume this many characters, we have to have seen a loop in the DFA. To be able to visualize this, we have state number 1, state number 2, and state number 3. To keep visiting new states, we need an A. It goes from here to here. Let's say this is the starting state. We don't know what states are final, it doesn't matter, that this is where we would start. By the time we consume the first A, we've seen a new state. By the time we consume the second A, to avoid creating a loop, we can't go back to ourselves, we can't go back to this state, so we have to go to the next state. But now there's nothing for us to do. We can't loop to this state, we can't go back to that state, and we can't go back to that state, because any of those create a loop. So we know we have to have seen that loop in a 3-state DFA by the time we consume the 3rd character in the string, when m equals 3. We don't know what m is here, but in general, we're going to carry this proof forward that says within the first m characters, we know we've seen that loop, because it is impossible to create a situation where you've seen more than m characters in a DFA. Each edge must consume at least 1 character. There's no way for us to avoid creating that loop. So a loop exists, it has to occur by here. So we know the length of that loop is at least 1 because we need a loop to be able to create an infinite language. Since there are an infinite number of powers of 2, if this language is regular, then we need a loop in the DFA. Great. So how do we move forward? In this case, we have 3 possibilities for what Y could be. It could be A, AA, or AAA. Doesn't matter where that loop is happening. The Y equals A could be here, here, or here, but it doesn't matter. Well, all that matters is the length of it. Because if you subtract or add A's at any of these points, it's going to do the same thing to the final string. If that makes sense. All right. So those 3 cases. What would happen if we subtracted an A? So basically we're saying when Y equals A, we're going to set I equal to 0. That means we're going to be removing an A from this string. That needs to still be in the language. Are the number of A's here a power of 2 if we subtract 1A? No. Is there a value of m for which that would be true? Yes. If we set m equal to 1, then the entire string is just AA. And if we subtract 1 from this, we end up with 2 to the 0. And since this says k is greater than or equal to 0, it's in the language. So we can't just use I equals 0 unconditionally, but it will work for every other instance of m that is not exactly m equals 1. Rather than subtracting 1, what happens if we add 1? In this case, that looks a lot better, right? If we add 1 to this, that means we're going to be looping whatever the loop of y happens to be here. And we're looping it an extra time. Is this a number of A's that's equal to a power of 2? No. So this works for m equals 1. Is there any value of m for which this doesn't work? If it were 2, and then we'd have 4 A's, we add 1 A to that, or 2 A's to that, and we'd end up with either 5 or 6. Neither of those are powers of 2, so that would work.
You just add 1.
Can you do, what do you mean by, can you just add 1?
Can you write for string so that it's a +1? Because no matter what power you choose, like there is no power of two that is just one above another power of two. Like if you choose two, you can set the power of two and then it'll be equal to four, which is also power.
Not true, unfortunately. If we choose m equals 0, 2 to the 0 is just a.
Plus would be two.
Of course, what this says is this is a zero-state DFA, which doesn't make sense. It is a power of 2, but we would need our DFA of some finite size to represent that. So m equals 0 actually does not make sense. So as long as you include either that, m equals 0 would be the counterexample to this, or you could go with the -1 and say there is one other case. If m equals 1, then what you should do is set I to a different value. Because I does not have to always be the same value. You just have to say, regardless of what this DFA is, how many times do I need to pump it? If the loop is of size 1, then if the DFA is of size 1, add 1. Otherwise, subtract 1. So you create a couple of cases out of it. So that's for the y equals a case. So the solution that we found for this is discuss m equals 0. And in general, we can just add 1 and we will be fine. So here we want to set I equal to 2. Because when we do x, y, z, again, I'll go back to that m equals 3 example just so you can visualize the string. When we add 1 to this, so now we're saying the loop is exactly 1a. We loop that twice rather than once. That adds 1a to the final string. That is guaranteed to not be a power of 2 unless m equals 0. But m equals 0 says the DFA is of size 0, which would mean that the language is empty. Or rather, it would accept maybe the empty string. But there's also no there's no starting state, there's no final state. So it doesn't make sense. So here is kind of what we found for the case of y equals a. Y equals AA. Let's take a look at that case. So y equals AA says that now the loop is going to be of size 2, which means that if we were to set I equal to 2, then we would be adding 2 a's to the string. If we were to set I equal to 0, we would be subtracting 2 a's. Right. Right. So now you have to split this down again into those two components where the special case is now something like m equals 1. As you add 2 to that, but any other possible power of 2. Well, we need to do it for all of these. Or I mean, setting it to I equals 3.
Yeah.
Is any power of 2
Actually,
6 larger?
no, or 6.
Because this is AA, if we're going to repeat this loop 3 times. I think that would work. I think that's a really intelligent use of I. Finding and thinking of what the length of this multiplied by what creates something that's never a power of 2.
With 5 also.
Potentially.
And 5 also.
Yeah. So let's say set I equal to 3 here. So we're going to create, I guess no, that would create 4 actually. So we want to set I equal to 4. Because this is going to do 3 additional loops of this. So we're adding 6 a's, or we're subtracting. There's no subtracting. We would say always set I equal to 4. And for any case where we could come up with a y equal to AA, this will always produce something that's not a power of 2. Adding 6 to any power of 2 does not produce a power of 2. What about y equals AAA? There's no power of 3 that is 3 more than another power of 3.
Is that three more than three?
3 more than any power of 2. Is that true? No, we can go from 1 to 4, right? So what happens if we set I equal to 3? Is there any power of 2 that is 6 more? Yes, 2 to 8. What about 9? Is there any power of 2 that is 9 more than another power? No, because 9 is odd.
Yeah.
There's no power of 2 that's going to be an odd number more than another number because they're all even. So how to finish this concept off is somehow figure out, no matter what the value of y here is between a and a to the m, we need some value of I that is always going to make sense, or some function that is going to determine what I should be. That means that we're always going to end up with something that's not in the language. This says that no DFA of size kind of 1 exists, because then y is forced to be that. As soon as you get down to here, you will say no DFA of any size can exist, because we know that loop has to happen within the first y characters of the string.
I think 5 is the lowest you can go. Or not 5, but 3, that's right.
Yeah. For 4, what can we do? How many times do you need to iterate this such that the difference between powers of 2 cannot be whatever that is? So I equal 1 would be the exact same string. So you're saying set I equal to 2 because it produces an extra 4. 0 to 4. 4 to 8. Oh, set I equal to 4. If we do this, what do we find? So this means 3 additional groups of this, we're adding 12. Is there any power of 2 that is 12 more than another power?
Oh,
Yes.
Yeah, 16 and 4.
Yes. 16 and 4. What about 5? So now we're saying, is there one that is 16 more than another? And 0 and 16 would work.
That works. I'm just realizing they say 4 and 5 together.
But whenever we have a 0, we can just discuss m equals 0 again, right? Because it doesn't make sense for there to be that. So we could do this and discuss m equals 0. So the only time that we get this extra power of 2 is if we go from m equals 0, which gives us a single a. When we add 16 a's to that, we end up with I guess now 2 to the 0 is 1. That would work. I don't even think we need to discuss m equals 0 here. It straight up doesn't work. So this is the thinking you have to go through for this kind of problem is now how do we generalize this? Is there a pattern between these i's? If we set I equal to 5 here, here, and here, would that work? Is there a general value of I that's higher than these? This is just kind of the first value of I, but is there a generic value of I? Maybe something that's based on m that would always be true here? Just trying to find some kind of generalization that says either yes or no. You can keep coming up with examples, but since we don't know how big M is, they're gonna be an arbitrary number of these. So eventually we need to find a pattern. Then we plug this back into that and say, all right, we said, let W equal A to the 2 to the M. So we can either use A to the 2 to the M minus 1 or A to the 2 to the M plus 1 to say that in general, even if we're adding up to A to the M of these, let's say we set I equal to 2 in this case, A to the M. So if we'd be adding at most M of these, if we add M to this, then we have 2 times A to the M. That's kind of that's what that means. Which would be this 2 times 2 to the M that's right here. So we can almost say that if we set I equal to 2 for almost all of these that are based on M beneath this, up to half of this, then none of those are going to work when we subtract. Because in order to get to the next power of 2 down, it has to be half the size. The next power of 2 up, it needs to be twice as big. So the solution to this depends on that principle or that thought, where you say, in order to reach the next power of 2, I need twice as many M's. The only way that I can get twice as many M's when we have A to the 2 to the M is to be able to add twice as many. And the only way you can add twice as many when I equals 2 is in this case. All of these other cases won't add enough A's. Does that make sense? If we're in this case, where now y equals A to the M, in order to get to the next power of 2 in this string, let's set M equal to 4, we need twice as many A's. If we set I equal to 2, there's no way that this size is ever going to be that size. This is always going to be shorter than that, except for maybe some weird side case, very, very close to the beginning. But we discussed what happens when M equals 0 and what that represents. So that's the tie that's gonna be able to polish off the problem. I want to be able to address other people's questions. So it's kind of was like, here's the direction that you want to go, but does that intuition make sense?
What's the final answer?
So the final answer is to go with these ideas, and you're going to want to say something that is of the form of, all right, regardless of the size of this is guaranteed to be less than this size. So whatever A to the M is, the size of y is bounded by at most M. It has to occur in the first M characters, not the first A to the M characters. Or sorry, A to the 2 to the M characters. So in order to do this, in order to get to this stage, we need A to the 2 times 2 to the M, which you can think of as this bar. And this M is never going to be as big as A to the 2. This is an additional copy of A to the 2 to the M. So you want to create an inequality that says that M is less than or equal to A to the 2 to the M. This bar is of size 2 to the M. This bar is of size M. When is this inequality true? In order to be able to pump this twice, you would need to find a case where this is equal. If it's never going to be equal, when you duplicate this, that's the concept of 2M is equal to 2 to the M. And there's only one case where that is true, at the very beginning of the sequence.
So we were, so this works because if you make N, or if you write out however many states that's for you, remember?
Yeah.
There is no way to continue without having the option of redoing it again, because that would because you have to allow for higher, what's it called? Higher numbers of M.
Yeah. Yeah, so you're gonna take this, see that this is at most size M. So you need some way of saying, this is capped by that, this is capped by that. We know this is always going to be true, except for one very weird case. That's never true. It's never equal to. So if you add an extra copy of this, we end up with 2M. How does 2M compare to 2 to the M? Whenever it is less than it, you can use I equals 2 to say I can't get to the next power of 2 by doubling the size of M. Or doubling the size of anything that is less than M. Because M is the highest that this Y can be. Does that make sense? Does that allow people enough to be able to finish it off? The wording at the end of it is very similar to what we covered yesterday. Is this the most useful thing that I could continue to cover, or Moses or Nathan, either of you have questions that I can answer ahead of tomorrow, aside from uploading the lecture?
Are we gonna have a full Chomsky in the exam?
A full CYK?
Yeah,
Maybe.
or Chomsky, I guess, yeah.
So, yeah, the only reason the Chomsky normal form is really used is to do CYK, that whole half 2D array. And that is on the study guide, so it is something that I could ask. Do note that even for my example in class, it took most of class to go through that example. So intuition would say that if I included something like that on the exam, it would have to either be such a small problem that there are only a couple boxes to fill, or that's going to be the entire exam.
Because if there is that, it is a big one that's gonna take up like 90%.
Yes. So then the next thing you would think of is, all right, our professor at least likes to think that he's a reasonably intelligent person and a reasonably fair person. So there is a project that is based on CYK and understanding CYK. That is the great outcome for that concept in class. So I am less likely to try to shove a CYK problem on the exam when there are other things on the study guide that there are no projects for that don't have a great outcome for. So if you're studying, I would say the biggest CYK thing I could put on there is very small. There are plenty of other things that I also need to ask you, and I recognize that we don't have a ton of time, especially in a 50-minute class for a 50-minute exam. So expect kind of one or the other.
Like when you go over the other differences between have a non-deterministic PDA and a deterministic PDA.
Yeah. So I should have had the study guide up on a second. I did.
To the bottom section.
Yeah.
Or before.
So difference between an NPDA and a DPDA. So an NPDA allows for non-determinism, which means that given a state that we are in, and a state is now a pair of the state in the push-down automata that we're in and the top of stack character. When we have non-determinism, we can have options for what to do when you're in one of those state tuples. So you can think of representing the state now as something like we are in state Q1 and the top of stack character is an S. This is a state because it's not quite the same if we're in state Q1 and there's an A on top of the stack.
Is it the same on the non-deterministic rules? Basically, it's like you have multiple choices.
Right, we can explore any number of options at the same time. If we're deterministic, then given this tuple, there must only be one thing we can do. So even in a deterministic PDA, we still allow for lambda transitions. We can still not consume characters from the input and or not consume characters from the stack. But we can't have, at any potential tuple here, we can't have multiple options of what we could do. We have to deterministically know where the next step is. There can only be one out edge from that graph, from that vertex in that graph, based on this combination of state top of stack pair.
You would want a, you can answer. Example. Yes.
That's pretty darn close. I would look into a little bit of this logic and say, are there any counterexamples to that logic? Does that fully explain it? But yeah, that is the proof layout type. That, yeah, start there, go through the logic, write the logic in a mathematical notation, some way that says, here are the constraints, here's why it cannot be true, and then say, I've derived the contradiction. So yeah, the end of this is going to say, I have shown now that L, this language, is both regular and not regular. I showed it's regular by assuming it, and I showed it's not regular via this derivation. It says that if it's regular, then there are some number of states where this is true, but I'm showing that there can't possibly be a number of states where this is true. So that's the contradiction. The only assumption that I made is that L is regular. Everything else logically flows. Therefore, the only thing that can be false is my assumption that L is regular. The opposite of regular is not regular. Therefore, we can conclude that L is not regular. Anything from your end, Ethan?
Not yet. Nothing specific.
I think the video from yesterday will help a bit more with polishing off of this. I'm kind of stopping at this point, but where to continue from here. We did one of those yesterday. Any other reasonably quick questions that I can answer? I will have full office hours after this, so I'm happy to answer anyone's question, individual questions or group questions in my office. Anything else? Anything else from the study guide? I guess we're basically out of time. So we'll do that exam thing tomorrow morning. If you have questions, follow me to my office.